Hi everyone, today I'm going to be doing the worked examples from exercise 5.4, which is differentiation of trig functions. So I thought first I would talk about why sine and cos derive as they do. So let's first look at when f of x is sine x. So I'll just make that a little bit bigger and let's draw a picture of a sine graph. So I'll just do the positive section. So this would be our sine graph, and well, there would be 0, there'd be 2 pi, here would be pi, and of course here is pi on 2, and here would be 3 pi on 2. So if this is y, or f of x, against x, well, let's see what the derivative graph would look like. So when we get to pi on 2, we have a turning point. So this is our gradient function, or of course f dash of x. So at pi on 2, we're going to have a 0 gradient because there's a turning point, and at 3 pi on 2, we're going to have a turning point. Well, we have a turning point, so we're going to have an x-intercept there on our gradient graph. So now we have to think, well, before that, we're going up the hill. So that's a positive gradient. So there, that will be somewhere there. The next bit, well, we're going down the hill until we get to 3 pi on 2. There we are walking down the hill. So that means we've got a negative gradient there. And then, of course, in the next bit, well, we're walking up the hill again until we get to 2 pi. So that's going to be a positive gradient. So what we see is that if we connect that up, this is a cos graph. So, and you can see that it's a positive cos graph, because a positive cos graph, it makes that U shape. So that's why if f of x equals sine x, then, well, f dash of x will be the positive cos graph. Now, if we go the other way, so let's look if we start with a cos graph. So again, I'll just do the positive part. And, well, here we have our turning point. This is 2 pi, and well, this is pi, and well, let's say it's f of x against x. So now I'm going to do the gradient graph. So I have a turning point. If I was to continue this graph going this way, this is a turning point here. So that means, well, there's a 0 gradient here at x equals 0. There's another turning point where x equals pi. And another turning point, if we were to continue, is at 2 pi. So now I can think, well, as I'm going from here to my turning point at pi, well, that's going down the hill. So it must be a negative gradient. So there it is. And then, as I'm going from pi to 2 pi, that's a positive gradient. So I'm going to be like this. And if we connect that up, well, we see the shape of a sine graph. And it's the shape of a sine graph, but it's the shape of a negative sine graph. So this is why we have cos. If f of x is cos x, well then f dash of x is going to be the negative sine. So it's handy to keep that in mind because, you know, you want to memorize which one's which. You want to be able to do it quickly, not have to draw them out every time. But if you understand it, you will not get it wrong. Let's move to the examples. And, well, here's another rule, and we'll see that as we go, whereby the derivative of tan is 1 over cos squared x, and that in turn is sec squared theta, or sec squared x in this case. This we can prove later when we do some of the different rules, but we're not doing that for now, so we're just going to accept this rule at the moment. So let's have a look. Here we've got sine 8x plus x to the power of 4. So I'm just going to say let y equals sine 8x plus x to the power of 4. And I'm going to do this just by using the rules. I'm not going to be using the chain rule for this one. We will be doing the chain rule in the next exercise, or the next chapter, rather. So what happens is, well, this is easy. Let's do that first. That's going to be 4x cubed. So then we're just left with this sine 8x. And we know that, well, the sine graph, like this, we're going up the hill first. So it goes to positive cos. What also happens is that this 8 here, whatever's in front of the x, or the derivative of the x, or the thing in the brackets, so the derivative of 8x is 8, and so we take that out the front. So 8 sine 8x is what we're left with, plus 4x cubed. So that means dy dx equals 8 sine 8x. And why this happens, why we take out the derivative of this and put it out the front, multiply it, is because of the chain rule. And we'll cover that a bit later. So there's the first one. Let's move down. And here, well, this one has a tan in it. And look, you can write tan as, so f of x equals tan x. Well, then our derivative is 1 over cos squared x, which is sec squared x. So I'll just write that rule out again there. And I'm going to go straight over to this one here. You can use the 1 over cos squared x if you wanted to. So what we do, we take the derivative of 5x. The derivative of 5x is 5. And we say, so let y equal tan 5x plus 2 cos x squared. And then, so that means dy dx is going to be 5 sec squared 5x. So I've taken the derivative of what we're tanning and I've multiplied it by, well, the derivative with the same thing in the brackets there. Now, well, the next bit, so the derivative of x squared is 2x. So we're going to say plus 2x times the derivative of cos x squared, or cos, the derivative of cos is negative sign. So remember, if you have this cos graph, well, the first thing you do is walk down the hill, so it's negative. So negative sine of x squared. So now, and of course we had a 2 in front of that as well. We don't want to forget that 2. So that means we've got 5 sec squared 5x minus, positive times negative is negative, minus 4x sine x squared. So this will be our derivative. And look, I kind of like it better when we learn the chain rule before we learn differentiation of exponentials and circular functions, but in Jacplus they don't do that. I did do a brief explanation of chain rule in the exponential differentiation, and we will, as I said, go through that in the next chapter. All right, let's have a look. This one looks a little hard, and a lot of people would think, well, I can't do it at this stage. It has a division sign or a vinculum, so, once you learn the quotient rule, you might think, the quotient rule would be appropriate there. And I mean, you could use the quotient rule, but this here, this 1 minus sine squared x, if you think back to when we did trig, well, let's draw a unit circle. And I'm going to make a little triangle here, right angled triangle, of course. And this is sine x, and this is cos x, and this is 1. So remember the Pythagoras rule here. So sine x squared plus cos x squared, so a squared plus b squared equals c squared equals 1 squared. So the hypotenuse is, of course, this line opposite the right angle, and it's a right angle triangle, so we can use Pythagoras. The, fancy way to write this is sine squared x plus cos squared x equals 1. So what that means is that, well, 1 minus sine squared x, if I minus sine squared x on both sides, I'm going to get cos squared x equals 1 minus sine squared x. And in fact, that 1 minus sine squared x is what we have in the top. So this is just a fancy way of writing cos squared x. So something else to note is that if you wanted to put into your CAS sine squared x or cos squared x. You need to put it in this form. So you need to actually put the brackets and then put the square. So keep that in mind as we, especially when we come to the application questions, I think that will come in handy. For the moment, it's the convention to write it like that, but it just means you're squaring the sine x. So let's go back over here, and that means y, so I'm going to say let y equal 1 minus sine squared x over cos x, and y equals cos squared x over cos x. And this is where it might be handy to remember that cos squared x is cos x squared. Because if you know that, then you also would know that you're just timesing it by itself. So it's cos x times cos x. And I mean, if you had x times x over x, you would know that you could cancel one of those x's there. And that's exactly what we will do. So we can, they have a partner, so we're left with y equals cos x. And we've done a lot of work to get to this stage, you know, a lot of thinking there, but we haven't at all answered the question because we're asked to find the derivative of the function. So if we want to find the derivative of cos x, well, that's really easy, but often people will just leave it at this because they've done a lot of work, so they won't realize they haven't actually answered the question at all. This is also a good reason why to call it let y equal that, because then on each line I'm writing the y, and I write the y on each line, so then I know that I still have not differentiated at all. I've only got y. So now dy dx, well, I can differentiate that, and if we think about cos, here's our cos graph. We're walking down the hill, so the gradient is negative, so it's negative sine x. So the reason cos goes to negative sine. All right, let's move on. And now we've got one that has a degrees. And what we need to know is that, well, we need to put it into radians. So, well, we're not going to use caps, we're doing it by hand. So I'm going to say let y equal sine 6x degrees. And, well, to convert degrees to radians, I need to times by pi over 180. So degrees to radians, that's what we do. So y equals sine 6 times pi over 180 x. So 6 and 180, it's going to leave us with 30 pi x on 30. So again, notice that I've let y equal our sine 6x, and then I've put the y on each line because I have not differentiated it at all. Now I can differentiate it. And I'm going to take the derivative of this. So this is just pi on 30x. So 1 times pi on 30 is pi on 30, x to the power of 0. You're just going to be left with the constant pi on 30. So I'm taking the derivative of that, and I multiply it by, well, sine. Let's look at sine. We're going up the hill, so that's positive cos. And nothing changes what's in the bracket there. It stays the same. So my derivative, dy dx, is just going to be, well, I'm just putting it together now. Didn't really need an extra line for that. And that is that. So there's our derivative function. Let's move on. Okay, so I think this might be the last one. Find the equation of the tangent to the curve y equals sine 3x at the point where x equals pi on 3. So really this is nothing different to what we've done in previous exercises. It's just that we've got a circular function. So the tangent, remember the tangent is that line, and it has the same gradient as the point, as the curve at the point. And in this case, it is where x equals pi on 3. And then, well, it passes through the point. And in this case, the point is where x equals pi on 3. The y value for that, we don't know yet, but we can find that out. Y equals sine 3 times pi on 3 plus 1. So, well, that's sine of pi. Probably should have left myself a little bit more room there. So sine of pi plus 1. Let's draw a little picture. There's pi. It's 0. So 0 plus 1. So it equals 1. So your y value is 1 when x is pi on 3. So now that we've got that information, we just need to find out, well, what's the gradient and what's the y-intercept? So let's find the gradient. Let's do a gradient function. So dy dx equals sine, remember, we're going up the hill, so it goes to positive cos. We take the derivative of 3x, which is 3, and we multiply it by positive cos of 3x. So I'm just going to put that in one line of working out. 3 cos 3x. The 1 will go because the derivative of 1 just is 0. And now, so now we can say we want the gradient when x is pi on 3. Three cos 3 times pi on 3. Well, that's 3 cos, these will cancel, of pi. We draw a little picture to be sure. The cos of pi is -1, so it equals 3 times -1, which equals -3. So far, we have y equals -3x plus c. So this is probably looking quite familiar now, hopefully looking quite familiar. Let's now find the value of c by, as per usual, subbing in the point. And the point is pi on 3, 1. So I'll sub that in. 1 equals -3 times pi on 3 plus c. 1 equals, this will cancel, neg pi plus c. c equals pi plus 1. So it looks a bit weird, but that's fine. It's not just a constant, which we often will find. But now we can say, therefore, the y equals -3x plus pi plus 1. And look, they might put this -3 last, you know, y equals pi plus 1 minus 3x, just so that you don't have the negative at the start. But really, that's just not necessary. You can if you want, absolutely not necessary. This is 100% a good answer and the correct answer. All right, that, I believe, completes the examples from differentiation of circular functions.